this video, we're going to look at population density and growth. So first, a population is a group of individuals of the same species in the same area at the same time. What that means is they're relying on similar resources, they're interacting with each other socially, and they can interbreed with each other. So let's look at our first way of describing populations, and that is going to be population density. Population density is a measure of how many organisms are in a defined space. So here you can see our formula is total population divided by total area. Now, low population density means there's fewer individuals, as we can see here with this forest, okay, versus a higher density where we see lots more trees in this same area. Now, number of individuals in an area only gives us part of the picture. We also have to consider distribution patterns within a population. So how are those individuals arranging themselves within the space? And this will provide us with insight into different environmental conditions and also social interactions within a population. So sometimes we might see completely random dispersion where those individuals are kind of located in different places at random. When we see clumped, which is often the most common dispersion, that might indicate more things about the environment. Okay, so it may be that perhaps there are certain resources that are allocated in different locations. So perhaps each of these little clusters of individuals here is clustered around, say, a certain type of food source. Okay, and that food source is kind of randomly dispersed, and so they're clumping around that. Or perhaps the clumping is due to, for example, like these wolves where they're hunting in, say, a pack. Or perhaps it's a prey and there's safety in numbers, and so they have a herd or a school or something like that to kind of keep themselves safe. So we often see that. And then when we see uniform distribution, it's often because there's a social interaction and we're seeing a territory where basically organisms are spacing themselves out to ensure that they have enough resources and space to, say, reproduce or obtain necessary food and water. Now, the key to figuring out population density is obviously having population size and your area. So let's talk about how scientists can actually estimate population size, especially when you're dealing with organisms that may or may not be moving. So there's going to be different sampling techniques for different types of organisms. Let's look at our first one, which is quadrants. So a quadrant is basically taking a grid and placing it over your environment, and then you can use kind of a random number selection to randomly select with which quadrants you're going to sample from. Okay, but in general, this sampling method is very good for organisms that are immobile, that are staying in one place and are going to stay in your one quadrant the whole time, and so you can count them. So here you can see as an example, they set up this a grid on a field, okay, and through, say, a random number generator, they randomly selected 5 to try to gather information about those individuals in those 5 little areas and kind of make a bigger estimate of population size. Okay, so to estimate your population size, you're going to take the average number of individuals in each quadrant and you're going to multiply it by the total area of that plot. And then you're going to divide it by the quadrant area. So basically you're setting up a proportion that's basically saying your number of individuals in your individual quadrant is going to be proportional to the total number of individuals in your entire sampled space. A similar kind of proportion can be set up with something called mark and recapture, and this tends to be used for organisms that move, so that won't stay in your designated area while you're counting them. So the idea of mark and recapture is you're going to mark your organisms. So that might be paint, a collar, some sort of tag, okay? You're going to mark them some way and then release them out into the population, okay? Now you're going to then recapture those individuals and kind of see how many marked individuals they are. And so this is going to allow you to basically collect and sample organisms that are kind of going to move and mix throughout the population. So here is another kind of outline of how this works. Okay, so let's say we have a sample of these ladybugs. We're going to put some paint on their back as markers. We're going to release those ladybugs back into the population. We're going to give them enough time to become dispersed amongst the non-marked individuals, and then we'll sample a small population from that. Okay, the number of marked individuals in our second capture should be proportional to the number of marked individuals in our total population. Okay, and that is what you're seeing down here with this formula as well. Now, once we have an idea of population size, we can then look at population size changes over time, which is population growth. And there are different patterns in population growth. Our first pattern we're going to look at is something called exponential growth. So when populations become established in a new area for the first time, they often show this rapid population growth, and that's due to abundant resources or a lack of predators or disease in that area. So we tend to see those individuals starting off with what we call like this lag phase, where it's a small population size, it's taking some time to be established, and then once it's established, it grows at this kind of continual rate. Now I want you guys to pay attention to the fact that for this graph, notice how the author here is making comments throughout the whole range of the graph. So when you have to write about population growth and you're talking about explaining what you're seeing in the graph, be sure to talk about the full range of the graph. So we're seeing this kind of lag phase initially, okay, and then let's say the population is doubling. So it's going from 1 to 2, 2 to 4, 4 to, and so on and so forth, up and up and up until we get this large population kind of established, where this kind of is this sustained growth, and there's a continual, like, constant rate of individuals being added to the population. Okay, here is another example of population exponential growth in a natural population. So this is the whooping cranes. They were nearly driven to extinction. And now, although they're not necessarily new to an area, because they have protections in place, so habitat protections, hunting restrictions, we are seeing kind of their population start to show that kind of upward curve. And so we tend to say that exponential growth has a J-shaped curve, okay? Slow initially, followed by rapid increase over time. Now, here is the mathematical formula for exponential growth. Again, this is under ideal conditions, okay? So this is our rate in growth, so the change in population size over time, okay? And we have two values we need to pay attention to, R and N. Ri stands for the intrinsic rate of growth, or the maximum rate of growth, and we're multiplying it by our population size. Okay, so here we can see this kind of ideal model populations where we have different rates of growth. We have a growth rate of 1 initially, and then we have a growth rate of 0.5, and you can see that is kind of changing almost essentially the slope of our graph, okay, and how quickly it rises. Okay, the faster the growth rate, the higher the population size over time. Okay, but naturally populations don't have all these complete protections. There are limiting factors to the population growth. So let's talk about those quick. Okay, limiting factors come in two different types. There's density independent and there's density dependent. Density independent limiting factors tend to be physical factors in the environment. Okay, they're things like changes in rainfall, temperature, or even catastrophic weather events like flooding, fire, volcanoes, things like that. And we call these density independent because it is they affect the population regardless of how dense it is. Okay? They have an equal effect at all the individuals. So if a flood comes through, it can wipe out an entire population of individuals. It's not going to, say, have a lesser effect on a less dense population than a more dense population. It's going to have an equal kind of death rate throughout. Density-dependent limiting factors, on the other hand, do have an influence based on density. So basically what that means is when there are fewer individuals in the area, we see a less of effect of these density-dependent factors. And the denser, the more individuals you crowd together, the more these factors come into play. So for example, food supply, when you have a dense population, there's going to be more competition for food supply. We might also see competition for things like shelter or water, whatever resources those individuals need to survive and reproduce. Something else that becomes density dependent is diseases and parasites. When you have more individuals in an area, it's easier for a disease to be spread. Okay, which is why with COVID-19, they suggest that we reduce density, say, inside of our buildings, and we space ourselves apart. We're trying to decrease our density so that it is less likely for the virus to spread between individuals. Another thing that is density dependent is predation. When you have a dense population, it is much easier for a predator to find and attack those prey. Okay? Versus a less dense population, the predator would have to be searching more to find individuals. Okay, so all of these factors are going to be influenced and increase the likelihood of competition, being found by predators, or the spread of disease. And all of those things would either, decrease births or increase deaths. So what are the effect of density-dependent limiting factors? We tend to see this other type of growth called logistic growth. Okay, logistic growth starts off with an exponential growth. Okay, there's initially, as the population is being established, there's kind of that lag phase, and then there's kind of a growth at a constant rate. However, when the population reaches something called the carrying capacity, the rate slows, and it often tends to fluctuate or stabilize around that carrying capacity. Well, what is the carrying capacity? The carrying capacity is the population density that can be supported in an environment under sustained conditions. So basically, it's a measure of how much resources are available for that organism. Okay? We call this kind of fluctuation around it, we call it that environmental resistance, those limiting factors that when the population gets too big, then disease, predation, or competition will knock them back down. So the mathematical model for this doesn't necessarily show that fluctuation. It shows a much nicer leveling off towards the carrying capacity. But let's take a look at this math equation. Okay, we still have this rate times our population size as we did before with exponential growth. But now we also have this portion right here. And this portion is taking into consideration K, or the carrying capacity. So that is, remember, the maximum number of individuals that can be sustained over a long period of time in our environment. So we're taking into consideration the need to kind of slow the growth towards that K, and slow it down. And we can really see the effect of those limiting factors versus, say, an exponential growth where there is no natural controls. Now, both of these are ideal mathematical models. This is not the way typically that organisms grow in their environment. So again, here's our nice mathematical logistic growth, But here are some examples of populations actually growing, and we're not necessarily seeing that clear pattern. So let's take a look at these little crustaceans here. You can see that both the blue and red population are growing exponentially initially, and then they kind of peak And then we see a drop and they start to level out. Well, what that indicates is that these populations have essentially overshot their carrying capacity. Okay, so they've gone a little beyond what their environment can support, and then some sort of density dependent limiting factor is knocking them back down, perhaps disease or predation. And then you'll see them kind of leveling off at what would be the carrying capacity. So oftentimes in nature, populations don't say, oh, I'm reaching my carrying capacity, I better reproduce less. Okay, that's not typically the case. Organisms are going to take advantage of the resources they have. And if the resources seem abundant, they're going to reproduce, but it may not necessarily be abundant for a long-term maintenance of that population size. And so that's why we're seeing that decline. So keep in mind, overshoots happen. Another thing that happens is you're not going to necessarily see this perfect slowing. Okay, oftentimes what you see is a fluctuation, especially in established populations. So here we have populations of hare and lynx. And what we're zooming in on is we're zooming in actually on this fluctuation around the carrying capacity. So essentially this part. We've already established, these organisms have already been established in the area. Okay, they've already grown exponentially, and now they're kind of growing. And what we can see is we often see these fluctuations because of predation, and predation is a density-dependent limiting factor. So our black line represents our snowshoe hare, and our red line represents our lynx. So if we take a look here, we can see that we have a sharp increase in snowshoe hares. And so their population is on the rise. Well, what that means then is there's now more food for the lynx. So shortly after, we see, a few years later, we start to see an increase in the lynx population because the lynx have more energy then, because they're eating more abundant prey. They have more energy to survive and reproduce. But when the lynx population starts to peak, that means our snowshoe hares are going to get eaten more, and our snowshoe hares start to decline. Now, with less food available, we're going to see our lynx start to decline then. And so we're kind of seeing this fluctuations, these increase and decrease. And they're essentially fluctuating around these straight lines that are drawn in. And those are our carrying capacities. So just understand that often in nature, we have fluctuations. Something else that can happen in nature is that carrying capacity isn't necessarily a set amount. Okay, so let's take a look at this deer population. So you can see we have some exponential growth, and then we definitely have an overshoot of our carrying capacity. So there are too many deer, and it's going to start to die off. Well, the problem with this large population of deer is that they're essentially eating the available food, and in the process, they might be, say, destroying the vegetation that's holding in the topsoil that allows for these plants to grow. And so basically an increased population size could degrade the environment. And so you can see the carrying capacity here is starting to really decline. So in the end, because there were so many deer and they decreased the quality in the environment, it made it say perhaps that there's fewer plants available for them to eat, the carrying capacity was reduced. And so as a result, there's going to be kind of a new limit to the population size. So carrying capacity can definitely change. And we see that with human population growth. Human population growth, if you look at this red line, is definitely showing that J-shaped curve, right? We're definitely seeing exponential growth. We have not seen the S-shaped curve, that kind of leveling off, that you would see with exponential growth, right? With logistic growth. Let's go back to this idea. So we often call logistic an S shape because we're kind of growing slowly, rising, and then leveling out again. So kind of like a stretched out S. So going back to the human population, okay, human population is definitely experiencing exponential growth. And for a long time, you can see for millions of years, our population size stayed relatively small and steady, okay? In kind of prehistory and early history, the earth just couldn't support as many humans. Okay, we were relying on nature for our resources, and so we had kind of a lower carrying capacity. But as human society has developed and we've kind of increased medicine, farming techniques, and other aspects of the Industrial Revolution, we definitely changed how much resources are available to the human population. Okay, we've shifted from, say, like hunter-gatherer lifestyle to more of a farming to more of an industrial lifestyle. And with that comes increases in populations over time. So humans have definitely influenced the carrying capacity of the earth for the human population. Okay, and so that's why we're able to see kind of a decrease in some of these limiting factors. Medicine takes away the limiting factor of disease, or at least decreases its effects. Okay, technology means we get more food to more people. Okay, and so we're affecting some of these density dependent factors, and that's causing us to kind of grow exponentially. Well, we know that in natural populations, exponential growth can't go on forever. So is the human population reaching its carrying capacity? Well, that's really to be determined. And there's choices we have to make as humans as to which path our future world could take. So here you can see right now, 2020, there's about 7.8 billion people on Earth. Now, in the future, that could continue. Okay, by in about 80 years, we could be at 15, 16 billion people, okay, on this planet. Now, will the Earth be able to support that many individuals, okay, with a high quality of life? That has to be determined. Or have we already reached our carrying capacity, as you can see down here, where we've kind of overshoot it and we might then begin to kind of slow and level out over time. We are definitely seeing the effects of density dependent factors on the human population currently, as we're in the middle of a COVID-19 pandemic. So we're seeing the effect of disease on population size. Okay, and we're also in other crises like the climate crisis and things like that, which are going to have effect on the amount of food and water resources available to the human population over time. So we really have to take into consideration how our human actions are going to affect the health and wellness of the human population over time. Now, I will say that the world population growth is slowing. So it is looking like we're either approaching our carrying capacity, okay, or we may have overshot our carrying capacity. Okay, but here you can see the annual world population growth is on a decline. However, that's not necessarily consistent throughout all countries of the world. So here let's look at this demographics. We're going to look at age structure diagrams. Now, the United States and other developed countries, like those in Europe and like Italy, we tend to have slow population growth or sometimes even zero population growth. So let's take a look at these diagrams and make sure we understand what they're showing. They're showing the relative number of individuals of each age. Okay? And so we can see that both in the United States and Italy, that the number of children, okay, are kind of at replacement or slightly below replacement. So what do I mean by that? Well, if you have a couple, okay, so two individuals have children. If they have two children, they've essentially replaced themselves in the population. If everyone is just replacing themselves, then our population growth should stop. If people aren't replacing themselves, so we have, say, a couple that only has one child, okay, they're not replacing both of them. And then if everyone reproduced that way, our population would then decline, as we see in Italy, where we have kind of this smaller base, where we have fewer children compared to older individuals. Okay, and so that type of population growth is going to be what's needed to get us to stabilize around our carrying capacity. But we are still seeing that there are countries in this kind of demographic transition where they still have rapid growth. And that has to do with the resources available to them. Countries like the United States and Italy, we have taken advantage of resources, and it has allowed us to have kind of a really great standard of living. And as a result, we have been kind of able to kind of control our population size, and we kind of have education and resources and things like that to kind of limit our population growth and ensure that those individuals that are born, okay, have the resources they need to survive. When you have a country in transition like Kenya, you tend to see that they have this much bigger base. And what that means is they're transitioning from a society where there may have been high infant mortality and high loss of individual life due to lack of resources or lack of medical care. And so as those are being made available to these countries, okay, we're seeing that more individuals are beginning to survive and reproduce. And so we're seeing this kind of a boost in young people. For example, Africa tends to have a very young population where the median age tends to be in the 20s. Okay, but all of those individuals, as they get into reproductive age, you have this kind of this boost in the population, and they reproduce. And if they're reproducing above replacement, we're going to see this kind of really big increase in growth. And so the population is going to continue. So we really have to consider that pathway forward. How are we going to do this? How are we going to ensure that everyone, every human on earth, has equitable access to resources and has opportunities for things like education, childcare, reproductive rights, to make choices about how their population will grow and how their families will grow over time. And also we need to make choices about how we're going to protect and conserve our environment to ensure that we have the resources available for these future generations to come.